Hi, I'm Jacques, and I'll be talking about optimal lower bounds for matching and vertex cover in dynamic graph streams, which is joint work with Christian Conrad. So, first things first, let's go over the problem definitions and make sure we're all on the same page. For both problems, we will have a graph G on n vertices. A matching in G is any subset of the edges such that no pair of edges shares an endpoint. Then a maximum matching is simply any matching which attains the maximum possible size. Meanwhile, a vertex cover of G is any subset of the vertices, such that every edge has at least one endpoint in the subset. And a minimum vertex cover is any vertex cover which attains the minimum possible size. We are interested in constant error approximation algorithms for these two problems. So, algorithms which, at least 2/3 of the time on any given input, will produce a correct n to the epsilon approximate maximum matching or minimum vertex cover, i.e. a matching of size no smaller than the maximum divided by n to the epsilon, or a vertex cover no larger than the minimum times n to the epsilon. Now, the computational model we want to study these problems in is called the dynamic streaming model. In this model, rather than being available in memory all at once, we receive the input piece by piece. Starting from a graph with a predefined vertex set and no edges, we receive a sequence of updates. Each update tells us to either insert or delete an edge from the current graph. For example, consider this graph on 7 vertices. We start with no edges. Then the first 3 updates arrive, each telling us to add an edge between certain vertices. Then we're asked to delete one of these edges, and so on. A streaming algorithm must process these updates and then be able to, on request, return a solution to the problem of interest on the current graph state. This model could represent, for example, social media data, with the vertices being account IDs and edges representing the presence of a friendship relationship between 2 accounts. As accounts friend and unfriend each other, the graph changes, and we may want to perform analysis on snapshots of this data. However, if there are billions of vertices, we may not be willing or even able to maintain the entire graph. So we judge performance based on the maximum amount of storage space the algorithm needs to use at any one time, and this is ideally much smaller than the full input data. We always enforce that the stream never tries to delete edges that are not present, and in our work we also ask that our streams are simple. That is, none of the intermediate graphs ever have multiple copies of the same edge. However, some of the prior work does allow multigraphs. While proving tight space bounds for this model is our main motivation, we also need to discuss 2 other related models. The first related model is the linear sketching model. Linear sketches are a special kind of algorithm where the algorithm state is linear in the input data. They can be thought of as a 3-phase algorithm. In the first phase, at initialization, the algorithm uses randomness to sample a linear map R from some special family. In the second phase, the algorithm applies the map R to the input data X. Exactly how this happens depends on how the data is received. It could be provided offline, all at once in memory, or it could be given in some distributed or streaming way. In any case, once the second phase is complete, the algorithm has some query procedure for extracting the desired output from the sketched data Rx. Similarly to the streaming model, we will judge performance based on the storage space required, specifically the space required to store Rx, the sketch data, along with the random seed used to generate R. The second related model is the 2-party one-way communication model. In this model, we have 2 parties that I'll call Alice and Bob. Alice has one part of the input, a graph called G+. Alice can perform arbitrary computations on her input with no bounds on space or time used, but can only send a single message M to Bob. Meanwhile, Bob has another part of the input, a subset of the graph edges called E-. He receives Alice's message and may also perform unlimited computation on his input and the message. At the end, he must output the solution to the specific graph problem on the graph consisting of G+ with the edges of E- removed. In this model, we will restrict ourselves to simple graphs, meaning no multi-edges. Sometimes people consider a private coin model, but we will allow Alice and Bob to have access to some shared public randomness. As with the other 2 models, we wish to judge the performance of a protocol and we measure this by the maximum possible size of the message m. But how are these two models related to the turnstile streaming model? Well, when I talked about linear sketches, I said the input data x may arrive in some streaming fashion. Indeed, every linear sketch is also a turnstile streaming algorithm with the same space usage. If x represents the adjacency matrix of our graph, then as long as we know r and the current rx, we can maintain the sketch under edge insertions and deletions by applying r to the adjacency matrix of the update and summing it to the previous rx. Similarly, every turnstile streaming algorithm is also a two-party communication protocol. If we simply view the edges of G+ as the first half of a stream consisting only of insertions, and E- as the second half of a stream consisting only of deletions, then it becomes clear that Alice can begin running the algorithm on her half, then pass the algorithm state to Bob as her single message, allowing Bob to finish running the algorithm. The message size is then exactly the algorithm space cost. So, we can relate the space complexity of any particular graph problem in the three models, as shown at the bottom of the slide, with upper bounds propagating down the chain and lower bounds propagating up. So now we understand the models, we can start to look at the previous results. As is the case with most turnstile streaming problems, the best known algorithms are linear sketches. For the approximate maximum matching problem, there are two papers released around the same time, which both show different approaches to attaining a randomized linear sketch for approximate maximum matching of size n to the 2 minus 3 epsilon minus little o of 1 bits. Both are based on a sampling strategy which is made possible by the existence of linear sketches for sampling from the support of a vector, known as L0 samplers. For approximate minimum vertex cover, the best known strategy is a simple deterministic sketch. Merge groups of n to the epsilon vertices into one, and then store the entire resulting graph. Solve minimum vertex cover exactly on the stored compressed graph, and then for each covered compressed vertex, cover all the vertices in the corresponding group, and this will give an n to the epsilon approximation. As we observed earlier, these upper bounds propagate down to the other models. On the lower bound side, the same Asadi et al. Paper that showed one of the approximate maximum matching sketching upper bounds also showed a complementary tight up to subpolynomial factors, sketching lower bound of n to the 2 minus 3 epsilon minus little o of 1 bits. Their bound works by taking advantage of the fact that linear sketches must also work in a different communication model called the simultaneous communication model. They also make use of Russo-Semeredi graphs, special graphs which try to pack as many large induced matchings as possible. Meanwhile, for the approximate minimum vertex cover problem, there is a footnote in a later work observing that the same sketching lower bound can be adapted to this problem, although this is not tight, as there is an n to the epsilon plus little o of 1 factor gap with the best known sketch. Both these bounds apply to the sketching model, but what about the streaming model? Unfortunately, no lower bounds were known specifically for the streaming model, and it looks like we're on the wrong side of the complexity inequality to learn anything from the sketching lower bounds. However, around the same time, there was a very impressive result published under the title Turnstile Streaming Algorithms Might as Well Be Linear Sketches, showing that, with some important caveats, the sketching and streaming models are in some sense equivalent. The upshot of this is that these sketching lower bounds can be lifted to the streaming model. Let's look more closely at this equivalence result. Roughly speaking, it tells us that whenever we have a streaming algorithm which is guaranteed to work for all streams up to an extremely long length, something like triply exponential in n, where the intermediate values of the input entries are allowed to become very large, something like exponential in n, then we are guaranteed that an equivalent linear sketch exists of roughly the same space cost, perhaps some log factor difference. In the original 2014 paper, it was also required that the streaming algorithm worked for streams where the input entries were allowed to become negative, but this condition was lifted in the 2016 paper. So what does this mean for the graph sketching lower bounds? It means if we want to make natural promises about the input stream, such as that it is simple, i.e. all the intermediate graphs are simple, or that it is only polynomial in length, then the lower bounds are not guaranteed to apply. There could potentially be a better non-linear streaming algorithm. We might hope that this equivalence result could be improved to remove these conditions, but there is a word of caution from a paper earlier this year. There exist natural graph problems for which violating either condition results in an exponential separation between the streaming and sketching models. Specifically, they demonstrate a triangle counting problem, which has a log n space streaming algorithm when the stream is guaranteed to only be big O of n in length, but is known to require omega of n to the 1/3 space to solve by a linear sketch, with a similar result for the other condition. So while it may be possible to shrink the length and entry size bounds, they cannot be removed entirely in general. So, to recap, there is an optimal linear sketch for approximate maximum matching, which is also optimal for streaming algorithms, as long as those streaming algorithms are guaranteed to work for very long streams with very large intermediate edge multiplicities. For approximate minimum vertex cover, there is the same lower bound, but the only upper bound is a simple deterministic strategy with a larger space cost. Our contribution is a pair of tight lower bounds for these problems in the two-party model. Any two-party protocol for approximate maximum matching requires sending a message of size at least omega of n to the 2 minus 3 epsilon bits, while any two-party protocol for approximate minimum vertex cover requires sending a message of size omega of n to the 2 minus 2 epsilon bits. These propagate up the chain, showing that the best known linear sketches described in the prior work sections are optimal up to log factors in all three models. Our proofs are surprisingly simple, essentially just consisting of hiding a known hard communication problem inside random graphs, in such a way that any method of returning a large matching of those graphs will leak information about the answer to the hidden hard problem. Notably, we do not need to make any use of Russo-Semerani graphs. Since we bypass the use of the equivalence result, these lower bounds hold even for streams where you make natural promises, such as the intermediate graphs all being simple, or the stream being only n squared in length. Now that we understand the results and the context behind them, I will spend the remainder of the talk giving a brief overview of how the two proofs work. First, we will look at the maximum matching lower bound. So, the general idea is to show that any protocol for approximate maximum matching can be used to solve another two-party communication problem called augmented index. Then, because this other problem has known hardness, we get a lower bound on the message size for our maximum matching problem. So, what is the augmented index problem? As before, we have two parties, Alice and Bob. Alice knows some binary n-dimensional vector x, and she's allowed to send a single message to Bob, as usual. Meanwhile, Bob has some index t in the range 1 to n, along with some partial information about the tail of the vector x. Specifically, he is told all the entries of x for indices larger than t, so x t plus 1, x t plus 2, and so on through the rest of the vector. Based on his input and the message received from Alice, he is asked to report the value of the entry xt and must succeed with probability at least 2/3. We know that any randomized protocol which solves arbitrary instances of this problem with probability at least 2/3 must send messages of expected size at least omega of big N bits. Now let's look at the reduction. So to recap, we want to describe how to transform a maximum matching protocol into a protocol for this other problem, augmented index. So let's assume Alice and Bob have access to some working maximum matching protocol. Now we fix a particular instance of the augmented index problem for vectors of size big N equals little n to the 2 minus 2 epsilon, where little n is going to be proportional to the number of vertices in our graph. Remember that this means that Alice knows the vector x, while Bob will know the index t and the tail of x. Now we have Alice build a bipartite graph between two vertex sets A and B. The green square over there on the left represents the adjacency matrix between the partitions, and we want the size of each partition to be roughly 8n. Next, Alice will embed the vector x into the yellow region of this adjacency matrix. She does this in a specific order, starting with the very first entry x1, placing it in the very bottom right corner of the yellow region, then x2 just to the left of x1, and so on along the bottom row. After the first n to the 1 minus epsilon entries are placed, we move up one row and again fill from right to left, and we continue filling in this pattern until the final entry is placed in the top left of that yellow region. Finally, Alice will use public randomness to hide the information she just embedded. This step is crucial in order to overcome any adversarial or biased behavior in the matching protocol that we've been provided. She does two things. She uniformly at random commutes the labels of all the vertices of both partitions, and she tosses a fair coin for every entry of the adjacency matrix. Then for each result of heads, she flips the corresponding bits of the adjacency matrix. Once she is done, Alice takes the resulting bipartite graph and feeds it into the provided maximum matching protocol to generate a message to send to Bob. Meanwhile, over on the other side, Bob receives the message along with the index t and the tail of x. By consulting the public randomness, Bob can reconstruct the vertex relabeling and most of the adjacency matrix. In particular, he knows all of the entries in the green area. Further, from knowledge of t, he knows the location in the adjacency matrix where xt was embedded by Alice, and this is shown here by the purple cell. Now consider the diagonal starting at the purple cell and continuing up and to the left. This consists of about 8n entries, about half of which should have been randomly flipped to a 1. So it should contain about 4n edges in expectation, and then by properties of the binomial distribution, it should be quite close to that expectation with high probability. Since Bob wants to recover a particular entry from this diagonal, he'd quite like it if this was the only large matching in the graph. So he's going to build a set of deletions consisting of all of the edges in the square containing this special diagonal, and this deletion region is shown here in black. As I mentioned earlier, Bob knows all the green entries from public randomness, but he can also reconstruct all of the entries highlighted in blue from his knowledge of the tail of x, and this will give him enough information to construct the entire deletion set. Once he's ready, he feeds the message received from Alice and the generated edge deletion set to the provided maximum matching protocol and inspects the output. Consider the matching obtained by Bob. Let's suppose that the matching protocol is always correct, or is at least correct with very high probability. Then if it includes an edge corresponding to xt, Bob immediately knows that its entry of the adjacency matrix had to be a 1, and so by checking public randomness to see if the bit was flipped or not, he determines the value of xt, and his task is complete. On the other hand, if no edge in the output corresponds to xt, then he simply learned nothing and has failed. So, what is the probability that Bob succeeds? Recall that the final graph contained a single large 4n-sized matching on the diagonal, so any correct approximate maximum matching must be of size at least 4 times n to the 1 minus epsilon. However, edges outside the diagonal are all restricted to 2 narrow bands of width n to the 1 minus epsilon, so they can only contribute matching of size at most 2 times n to the 1 minus epsilon. Therefore, the protocol, if it gives a correct output, must provide at least 2 times n to the 1 minus epsilon edges from the diagonal. Now, observe that due to the random relabeling and flipping, it would be impossible to figure out which entry on the diagonal a particular edge corresponds to by only inspecting the insertions and deletions given to the matching protocol. Any given edge is equally likely to correspond to any of the entries along that diagonal. Therefore, no matter the behavior of the matching protocol, Bob will learn the locations of 2 times n to the 1 minus epsilon ones from the diagonal selected uniformly at random. Given this, and the fact that the purple cell is a 1 with probability a half, we know that the overall chance of being able to discover the state of xt is at least 1 over 4 times n to the epsilon. So we simply perform this whole procedure, order n to the epsilon times in parallel, and at least one will succeed with constant probability. This blows up the message size by a factor of theta of n to the epsilon, so the omega of n to the 2 minus 2 epsilon lower bound on augmented index becomes a tight omega of n to the 2 minus 3 epsilon bound on approximate maximum matching. A little more work is needed to show that this strategy works even for protocols that only succeed with constant probability rather than high probability, but this is essentially the entire argument. The reduction for minimum vertex cover works very similarly. The key difference is that Bob now also deletes the diagonal above and to the left of the purple cell where xt was hidden. The resulting graph then has a small vertex cover of size 2 times n to the 1 minus epsilon, consisting of the n to the 1 minus epsilon vertices at the bottom of the A side and the n to the 1 minus epsilon vertices on the right of the B side in the diagram. This means that any correct approximate vertex cover can consist of at most 2n vertices. In particular, only 2n of the entries on the deleted diagonal can be covered. If the purple cell is a 1, then it must always be covered. However, if the purple cell is a 0, then it is indistinguishable from the other zeros on the diagonal, of which there are at least 4n with high probability. Only 2n can be covered, so the purple cell is covered at most half the time. By repeating a constant number of times, we can look at only the occasions when xt was not flipped, and identify whether it was always covered or covered only half the time, to determine its value. As we only use a constant number of parallel repetitions, we get the tight bound of omega of n to the 2 minus 2 epsilon. Thank you very much for listening.